Okay, let's start. So in the last class, we essentially saw what happens when you take an endpoint DFT for a sinusoid, and based on the discussion, we saw how to choose an appropriate sinusoidal frequency to test your circuit. And the bottom line was that when you take an endpoint DFT, you need to ensure that the signal falls on a frequency bin. And tell me, if I take an endpoint DFT, what is the bin width? 2 pi by n. So my discrete time sinusoid must fall on a bin, which means the sinusoid must be of the form m times the bin width. So which means the continuous time frequency, how should it be related? Yeah, m by n times fs, right? So this is how you choose your continuous time frequency, so that after taking DFT you don't have major issues. And it is not just enough to choose this to be of the form m by n. Yeah, we also need to choose m by n to be co-prime. There should be no common devices between the two. Fine. Of course, in simulation this is quite easy to establish. You just feed the number as it is and the simulator will take it. But this is not possible in practice when you measure. So in that case, the signal will not fall on a bin, and that results in a spectral leakage. And the solution to reduce the spectral leakage is, as we saw, windowing. Again, the reason is when you have a signal that is not falling on a bin, and when you take an endpoint sample, the sinusoid will not complete integer number of cycles within the chosen endpoints. So which means when you form a periodic repetition of the signal, you will have abrupt jumps around the edges. So the notion behind windowing is to basically smoothen down those abrupt jumps, right? And two commonly used windows in circuits is essentially Hahn and Blackman-Harris, and we saw the cons or the downsides of using windows. So now basically you know how to test an ADC. If I give you an ADC, you know how to characterize this ADC's metric, and the only metric we know as of now is the effective number of bits, or SQNR as a proxy. So you feed in a sinusoid with the maximum amplitude with a frequency like this, and then you take the power spectral density at the output, measure the SQNR and back calculate E naught from this. Right? Cool. And let's say if this is a 10-bit ADC, how much is the SQNR I expect maximum? About 60 to 62 dB is typically what we expect, right? 6n plus 1.76, right? And yeah, so let's see if that is indeed the case. So I went ahead and tried to do a simulation in MATLAB, and I again have to choose my frequency to be of this form. So first I choose the number of points of DFT that I am interested in, and that is generally up to you. Essentially, larger you take, the better is your estimate, because you are finding the noise power by summing up all the bins, essentially ignoring the signal bin. So like any statistical measure, larger you take, better is the estimate. But again, you can choose it to be anything. Typically few hundreds is more than enough. So here I chose to be 1000, and I chose my input to be, I think, 91 by 1000 times Fs. Of course, they are co-prime. So and then I take the output spectrum. So here I am plotting the power spectral density. So actually I am plotting the power spectral density scaled by the number of points in decibels. Okay. Fine, and I'll just say n is 1000. And x-axis is the bin number going from 0 to n by 2, 500. Okay. So remember, if I take the power spectral density and scale it by the number of points, what measure that gives me? I mean, if I sum up all the frequency bins and scale by n, what do I get? Power. So if I scale the power spectral density by n, that directly gives me the power at each frequency bin. That's all. Fine. So here the sinusoid is like this, -1 to +1. So what is the expected power of this fellow? 1 by 2. In log scale, how much is this? You like 10 log of the power, that is -3 dB. So that's what you expect. So yeah, 91st bin you get minus 3 dB as the power, and that's to solve the quantization noise. Yeah, because I've chosen the signal to fall on a bin. It's a simulation in MATLAB, right? And again, you have to use window even if the even if the signal falls on a bin, only for noise shaping ADCs. For other ADCs, this is more than enough. So again, let's quickly do a back of the hand calculation and see what is the SQNR. So again, first, sorry? No, right? I mean, you can see, just because you know something doesn't mean you have to use it always, right? We need to use window if the signal is not falling on a bin. It is a nice simulation, everything is ideal, so I can choose it appropriately, so there is no need to use window. Of course, you can use it, there is nothing harm. To kill a mosquito, you don't take AK-47 and kill, right? Something like that. You can use it, but it's an overkill. Yeah, so again, first you see that signal is fine, and quantization noise spectrum is kind of flat, right? Reasonably good. So, so here, let's say I approximate it to some flat number. So say this about minus 90 dB or so, reasonable. So let's approximate all the bins to be at this level. So can you find and tell me the quantization noise power from this? How can you find? How will you find the quantization noise power? Yeah, except that bin. I mean, that is basically sum up 499 bins. 500 or 499, it's basically nothing. So how do you find it now? I am saying this level is minus 90 dB approximately, all the bins. So how do you find? Minus 90? I mean, first of all, how do you find the noise power? Tell me in words. Add up all the parts in each bin. So that is in absolute scale. So if basically let us say each bin is of some level, some x. How many bins we have for noise? Yeah, let's find that it's okay. Quick calculations you are interested in, right? And I have to take 10 log of this quantity, right? I already know 10 log of that x. That is minus 90. 10 log 10 of 500. So what is this? 10 log 10 of 500, how much is it? I mean, see, just you're engineers, right? No need to crunch in numbers. 500 is 1000 by 10. 10 log 1000 is how much? 30. 10 log 2 is? No, 10 log 2. Come on, people. What is minus 3 dB bandwidth? 1 by root 2, you take 20 log of 1 by root 2 is minus 3. So 10 log of 2 is? Okay, 20 log of 1 by root 2. I mean, see, you should be able to do quick calculations. This is minus 3. So 10 log of 1 by 2 is? Minus 3. So 10 log 2 is? 3. Okay, fine. So tell me now what is 500 log 10 of 500? 57. 10 log 1000 minus 10 log 2. Fine. This is fine. This is 1000 by 2. So that is 60 minus 3. Okay. So this is basically minus 90 plus 57. Is that correct? Oh, sorry. Yeah, I'm sorry. I'm really sorry. Yeah, that's what I was thinking. Something is way off. Okay. Thanks. Just to make sure you're all correct. Even you are following me, you made an intentional mistake. If I make a mistake, I can say like this and escape, but you can't. Okay. So this is roughly how much? 63? Yeah, dB. Thanks. Yeah. So now signal power is minus 3 dB, noise power is minus 63 dB. Signal to noise ratio is not, how is it very small? How much is it? 60 dB. Fine. For a 10 bit, that's typically the expected number. I mean, this is a rough calculation, right? So a couple of dB error, it's okay. See, if someone says that this is a 16-bit ADC, you can vehemently deny that that's not possible. The whole point of engineering is to just look at things and make some quick approximate calculations. Okay. So from this we can say it's about 60 dB and that's about 10 bit now. Okay. Fine. So of course now I have given this. Let us say I do ask you to do the opposite. Let us say I tell you it is a 10-bit ADC and I ask you to plot the spectrum. You should be able to plot this. Here I did the opposite. I gave a spectrum, ask you to compute the SQNR, you should be able to do the same reverse also. I give you the SQNR, you should be able to roughly sketch the spectrum. And that's what your assignment is also about. Anyways, yeah. So now, in practice, it turns out, in addition to the quantization noise, you also have circuit electronic noise that also turns out to have a flat power spectral density. So in practice, you cannot just measure signal to quantization noise ratio. You will be measuring the total noise ratio that contains the signal, quantization, and thermal noise. Cool. So,
in the previous plot, we took minus 90 dB and went along with it.
Correct.
So, but we saw that for the quantization noise, many levels were below.
Yeah, it's a rough thing, right? Basically, if you want to approximate with a flat thing, this is a reasonable thing. If you want to do it exactly, you have to sum up all the bins and do. What I'm saying is, from this plot, this might be a reasonable. So, yeah. So in addition to this, it turns out we'll be making these ADCs using transistors. A transistor is a linear device or a non-linear device? Non-linear. So if you make a circuit or a system with a transistor, will that be a linear system or a non-linear system? Non-linear system. So if you don't design it properly, you will also have severe non-linearity. So that means that if I apply a sinusoid, ideally, as of now, we expect to see the sinusoid at the output spectrum and a flat portion corresponding to quantization noise, thermal noise. In addition, if the circuit is non-linear, what do you expect to see in the spectrum? So which means, distortion in spectrum, you will see the harmonics of the input sinusoid. So we will see second harmonic, third harmonic, and so on. Right? So the output will no longer be my input plus quantization and thermal noise. We will also have, let us say, alpha 2 y squared, some alpha 3 y cube, and so on. So to capture this non-ideality, we measure what is called SNDR, that is signal to noise and distortion ratio. Sometimes this is also called as SINAD, again signal to noise and distortion. So this here you include everything, the quantization noise, thermal noise, and power of all the distortion products, right? So this is the ultimate measure that captures all the non-idealities in the circuit. So you measure this, and then from this you back calculate what is the ENOB. So ENOB is same thing, you find it from SNDR. So many minutes.
So when we take the thermal noise, that will be SNR, that part.
Yeah.
And then we take all the distortion and everything, that will be SNR. Like
yeah,
SNR.
correct. Yeah, correct. The name should be obvious. This contains only noise. This includes both noise and distortion. So again, let's see what happens. So I took the same ADC, the one I showed here. I introduced third and fifth order nonlinearity. So we expect to see third and fifth harmonic, right? So I did that same setup. So the input is at 91st bin. Third harmonic is at 3 times this, 5 times this. Okay. So here, can you tell me what is my SNDR approximately by just by inspection? SNDR is sum of this noise plus these fellows. I already told that this is a 10-bit ADC if you don't consider the distortion. So what is the noise power roughly? Let us say PQ is minus 63. Signal is at minus 3. So roughly the noise power is expected to be at minus 63 dB. And look at the strength of the harmonic, third harmonic here, minus 51. That is at least 10 dB higher than my noise power. 10 dB higher means in absolute scale, how much is it higher by? 10 times higher. 10 log is what we are plotting. So in absolute scale, this fellow is 10 times higher than everything. So the sum is dominated by this guy. Clear? So the SNDR is essentially now the difference between these two fellows. That's it. Yeah, last is you can see, but that is again minus 69 dB. That is lower than my quantization noise, so it might not affect you so much. Is that clear? Again, these are all quick back of the calculations. Something you should be able to do. So what is the SNDR now roughly? Huh? How is it 2? This is minus 51. 49. Yeah, I mean ratio, but in decibels it is a difference, right? This is all in decibels, mind you. This again, sparse spectral density scaled by the number of points. N is 1000. So it's about 48, 49 dB. So what is the E knob now? Huh? Around 8 bits. Okay? This clear? I mean, you should be able to make reasonable approximations in practice. Okay? Cool. So one thing is, see here I am plotting the spectrum, and let us say the fifth harmonic is visible, but it is not so distinctly visible from the noise floor. We'll call this as the noise floor. Okay. Now let us say the same thing, if I want to observe this fifth harmonic more distinctly, let us say I want to make this fellow not increase, the same ADC, I am not increasing the nonlinearity. Let us say when I am measuring it, I want to see this more distinctly above the noise floor. Is there something you can do while plotting the spectrum? Or let me rephrase it this way. Right now my noise floor is this much, right? Yeah, this is the noise floor is this much and the distortion is this much. I want to make sure that this is distinctly visible above the noise floor. Okay, so now maybe say, let us say this is my model, right? Y plus say alpha 3 y cube, alpha power 5 y power 5 plus noise, right? So the strength of this fellow is determined by this nonlinearity, right? Who is determining this level? It is just Q, or what is it? How? What is this determined by? Huh? What do you mean by average of Q? Q has zero meaning.
Average power.
I mean, when you say power, there is. I mean, is it just the quantization noise? Basically, this level you are saying is equal to the quantization noise, or something else? How do you find the quantization noise from this level? I mean, let us say all the bins are at this level, right? Made the approximation. How do you find the quantization noise? Sum of all the bins. Sum of all the bins is fixed. So what is this level determined by? It is a quantization noise divided by number of points we take. Is that clear? Sum of all these fellows is constant, that is delta square by 12, whatever. This level is that noise power divided by the number of points you take. Fine. So if I want to reduce this, what can I do? Increase the number of points. Clear? The same noise is there. If I take larger number of points, that noise floor will reduce because we are summing up over a wide range of n. Fine. So I did that. I basically increased n by 10x. So this is basically 10,000. As you can see, this is going till 5,000. So now you can see that these fellows are, I mean, at least the fifth harmonic is more distinctly visible. The level of, I mean, the strength is the same, right? Earlier it was 69.7, that's about 70. The same. So earlier the frequency was 91 by 1000. Right now I have chosen it to be 911 by 10,000. Input frequency is roughly the same. Clear? So this is something to have in mind. The noise floor here, it depends just not on the quantization noise or the total noise power. It is the noise power divided by the number of points that is in your spectrum. Okay. Cool.
This will make any significant changes in our
nothing. The calculation, nothing changes, right? But let us say you want to observe.
Okay. Just for the sake of observation.
Yeah.
The total signal power would be the sum of that all those harmonics, right?
No, signal, this is the signal. This is the known, this is the desired part. This is not something you want, right? The harmonics is not something that you want.
So we won't add them.
When you are finding the noise power, you ignore it. But the final deal is you find SNDR, noise and distortion, right? So here you take the ratio of the signal power by everything else, including noise, distortion, anything else you have, you include it. Okay? Is that clear?
SNDR is also known as sinusoid.
Yeah. People give different names. Those are not something I don't want you to remember all those jargons, right? The underlying principle is what is important, right? Okay. Cool. So now let us say I keep increasing this input frequency here. What will happen to the harmonic frequencies? No, if I increase the input frequency, what will happen to the harmonics frequencies? They will also increase, right? And if I keep increasing beyond some point, what can happen? Yeah, basically if I keep increasing this frequency, all these guys will go. After some point, this guy can go beyond fs by 2 and it will alias back. Fine? Remember, we are plotting the spectrum from 0 to n by 2. In discrete time frequency, it is 0 to pi. Continuous time frequency, it's 0 to fs by 2. So if the harmonic goes beyond fs by 2, it will alias back. And I have chosen a case like that here. The same ADC, nothing changed. I have just changed the location of the input frequency. So third harmonic will be at what value now? 1011 times 3 is how much? 3033, fine. 1011 times 5 is 5055. My thing is from 0 to 5000, right? So where will this alias to? No, remember my number of points is 10,000. Where will it alias to? Huh? Yeah, remember this is the thing, fs minus delta f will alias back to delta f. When you map it to the DFT parlance, fs maps to what value of bin? No, in DFT, when I take the bin, what bin number fs will map to? N. So let us say this is plus or minus some capital, I don't know, L. This will alias back to L. Fine? Same thing. So this will map to basically 10,000 minus something. This is 5055. This will map to this value. So it will alias back to 10,000 minus 5055. You do this, this is 4945. Right? And that's what you see. Fine? Okay. So again, so now you see when I kept increasing the frequency, the fifth harmonic fell back here. If I keep this further and further, third harmonic will keep increasing. This fellow will come lower and lower. After some point, what can happen? They not overlap, but yeah, fifth harmonic can go here, third harmonic can come here. That is, if the frequency is such that the third harmonic is not aliasing, but the fifth harmonic is aliasing, and it can alias to a frequency lower than my third harmonic, right? And again, I have chosen a case like that here. So the input is, again, ADC is same, I have not changed anything, just that input I have changed. 1501 times 3 is 4503 within the range. So 1501 times 5 is 7505, and this you can calculate aliases to this. Again, this 10,000 minus whatever 7505. So again, sometimes if you just look at the spectrum, it might look counterintuitive because you expect that as you go to higher frequencies, the harmonic strength should reduce. But here it looks like, this fellow seems to be lower and this fellow seems to be higher. But the point to note is, just because this is at a lower frequency doesn't mean that it corresponds to a lower harmonic. This is some higher order harmonic that has aliased back to this frequency. Is that okay? So please be comfortable in these things. Okay, so I'll maybe show one example from the paper. So this is a paper from last year, from Journal of Solid State Circuits, which is where all the best chip design works are reported. So again, the title might not make any sense to you right now, but before mid-semester you will be able to understand everything in this. So this is by the way from Intel, okay, shown here, both from Intel US and Indian teams. So I just want you to focus on the spectrum. Yeah. So let's say look at the spectrum to the left, right? So this here the sampling rate I know is 3.8 gigahertz. Okay. The input frequency is chosen to be about 0.2 gigahertz. It is not exact, approximately 0.2, so that it's falling on a bin and stuff. So where do you expect the second harmonic to be? 0.4. Again, see, this is basically a DFT, but they have mapped it back to continuous time frequency. Okay, starting from 0 to fs by 2, that is 1.9. Because bin number doesn't make a lot of intuitive sense, you map it back to the corresponding continuous time frequency in the final thing. So 0.4, so that is somewhere maybe here. Third harmonic is 0.6, somewhere here, and that is the reality also. Magic. Okay. So yeah, SD2, SD3. We have other things again. Before mid semester, we'll be able to understand what these tones are. So this is a simpler case. Now let's look at this thing. Same thing. Sampling rate is 3.8 gigahertz. Okay. The input frequency is 13 gigahertz. So this will definitely alias back. To what frequency will this alias back to? Can you calculate and tell me? You can work out and tell me. You can wait for a minute also. 9 is also greater than fs by 2, right? Or maybe, yeah. Think about it, 2.4. No. My fs is 3.8. The maximum frequency I can have is 1.9. Oops. So 3.8 tables. 3.8, one is 3.8. 1.6 or 0.6? So I have written the 3.8 tables here for your reference. 1.6, everyone is fine? Remember, this is 3 times 3.8, yeah, plus whatever, plus 1.6, that is 13. Basically, you take 13 and divide, subtract it with m times fs and keep increasing m till whenever it falls back to fs by 2. That's the thing. Okay. Everyone is okay? Yes. Fine. So yeah, that's where you expect. Voila, that's where you see the frequency also about 1.6. This is 1.5. So this is Fn is 1.6. Second harmonic will lie at what frequency? 1.6 times 2 is 3.2. 3.2 is definitely beyond my fs by 2 of 1.9. So where will it alias to? 3.8 is fs, by the way. I have a frequency 3.2. Where will it alias to? 0.6. Okay, here it's just fs minus that thing. 0.6 is somewhere here. Yeah, maybe this one. Third harmonic will be 3 times 1.6. That is 4.8. 4.8 will be around 1. 4.8 minus 3.8 essentially. So that's about somewhere here. Somewhere around this point. So again, I'll do a magic eraser and you will see everything. So SD2 is, oopsie, yeah, SD2 somewhere here as expected around 0.6 and SD3 is somewhere around 1 gigahertz. So yeah, please make sure you are comfortable in calculating these, because I mean, it is one thing to make a circuit, but if you are not able to measure it and say this is what my circuit is doing, there is no point. So as you see, I'm not teaching you just for the sake of my pleasure to make you learn more things. This is absolutely essential finally when you are characterizing and reporting this. Okay. And these high-speed ADCs will be used in all your like USB, LAN, everywhere. Okay, that is another metric. Okay, it turns out you can have other tones. I mean, right now you expect that you have signal, you have its harmonics. Because of random reasons, we'll see later, you can have other tones also, which is not related to the harmonic. Some other tone, let us say, comes up. So SFDR is basically it's called spurious free dynamic range. So it is the difference between your tone and the highest spurious tone, unwanted tone. This unwanted tone need not be harmonic, it can be anything. So it's all definitions, it's not like a major thing to remember and stuff. Okay. Is that fine? So hopefully you are all comfortable with basic plotting of spectrum and finding out where each thing will alias back to blah blah blah.